All right, this is the video for the worksheet related to energy flow diagrams, where students are supposed to identify the different kinds of energy stored in a system and see how that energy flows over time as the system does something. Um, in our class, and you can see on the screen, we have adopted the idea that there are 5 different ways energy can be stored. The first 3 are called mechanical energy, and they are kinetic energy, potential gravitational energy, and potential elastic energy. These 3 kinds of energies have formulas you can use to calculate them. Although today we're not going to calculate the energies, we're just going to estimate the energy in percents. It is advisable that in the future we will use the formulas to do calculations. The other 2 energies are the internal energy and the chemical energy of the system. In general, when a system does something mechanically, like moving, going to a higher place, or being stretched or compressed, that energy after being used will be dissipated to the atoms due to air resistance and friction. So all the mechanical energy eventually becomes internal energy. That's why we call internal energy the graveyard of all energies, because they end at that place eventually. Right? So we're going to see the first example, which is a ball that is being dropped. But it's important for us to first make a parenthesis here. When you're analyzing the energy of a system, you need to define the system correctly, or at least make a convention of so how people will select the system. So in our case, everything in the picture will be considered part of the system. So everybody can get more or less the same results. So we can be consistent with our answers. So when you have the system represented by the picture on the left, you can see a ball being dropped from rest. And we're going to restrict the analysis to the ball moving in the air before it hits the ground. As you can see at point A, the ball is just being released and the kinetic energy is 0 since it's not moving. So we're going to write down the values in percents on each of the columns you see there. Every column is representing points A, B, and C in that order. So I'm going to have to get off the presentation mode so we can do that here. Alright, so for point A is the highest point, but it haven't started moving yet, so the kinetic energy is 0. So if you look at the ball, you see the ball is not burning, so there's no chemical energy released, so this one is going to be 0 also. And the ball is not being compressed or stretched, so we can say that the elastic energy is not present. Alright, so the atoms inside the ball and the air around are moving. So we will assign certain amount of internal energy. Remember, internal energy is the energy of the atoms and molecules moving inside a substance. And the only way they will not have internal energy, or the internal energy is equal to 0, is when the temperature is so low that they don't move at all. And that is what we call absolute 0. Any temperature above absolute 0 will be representing a certain amount of internal energy. So what is absolute 0? Well, it's 0 Kelvin, which is equivalent to minus 276.15 Celsius degrees. So it's very cold. Since everything we do around us, objects around us are above that temperature, we need to assign certain amount of temperature, certain amount of internal energy to a system So um, let's consider that the internal energy is about 1% of the total energy of the system. That means that we have 99% of the energy stored as potential energy at point A. As the system evolves over time, the ball has more time to go through air, and there is air resistance. So some of the energy of the ball will be dissipated to the atoms because of the air resistance. So the internal energy of the atoms in the ball and the air around will increase. So let's say that for point B, we can assign a number 2% of the energy. And for point C, we can assign number 3% of the energy will be stored as internal energy of the system. Okay, the elastic energy of the system will remain 0 for all the points, same for the chemical energy of the system. But at point B, the ball is already moving certain amount. You can see the arrow pointing down there. Also, it lost some height, so we're expecting to see less potential energy, and since we have no numbers, we will estimate this to be maybe 50% of the total energy. And so the 50% of potential energy and 2% of internal energy, that's 52%. The rest will be kinetic energy. 52%, 48% for kinetic energy. So 48 plus 50 plus 2 should be equal to 100, which is 100% of the energy, the total energy. All right, so when you analyze what's going on point C, you see that the arrow for velocity is a longer arrow, and that the ball is barely at the ground, or almost out the ground, but it's not touching the ground yet. So it's still moving. So it has lots of kinetic energy, almost no potential energy. So I will assign a 1% to the potential energy, and that gives me the result I'm looking for. So 3 plus 1 is 4, 100 minus 4, 96. So 96% of the energy is in the form of kinetic. When you add up the numbers, you get 100%. And so that's the way you assign different percents to the energies on a system. So that's the answer for number 1. Let's do another one. We have number 2. Number 2 is a wind-up toy, and it's warm up, and then you put it on the surface of the table or the ground, and then it walks. Right? So since it's moving in a horizontal surface, we can establish that level as the 0 high. That makes the potential energy equal to 0. And since it's moving horizontally, it's always 0. Also, the wind-up toy is not burning. There's no chemical energy released from there. So we can establish the chemical energy equal to 0 for all 3 points. Now let's assign 1% of internal energy on point A, and since it is already moving at point A and it has some energy on the spring, that's the one that makes it move, I can assign numbers to kinetic energy and elastic energy. Let's use even values, right? So we're gonna do 49 for kinetic energy and 50% for elastic energy. That adds up to 100. At point B, you can see that the arrow for velocity is shorter, so that makes it moving slower. And at the same time, it's been moving from point A to point B, so it uses up some of the energy on the spring. So the expectation is that that energy on the spring will not be 50%, but maybe it's being cut to 20%. Same for kinetic energy. Let's make it 20%. And as you can see, the rest of the energy is already stored at the atoms as internal energy, and that will be a 60%. If if you analyze what's going on at point C, you can see that at point C, the toy is not moving. So the kinetic energy is assigned to 0. And but I don't know if you noticed that, when I was a kid and I was playing with these toys, if the toy stops moving, but you lift it, you still can see this some energy in the system, but it's not enough to move. So the spring still has some elastic energy. It's just that it is not enough for the system to move. But I will assign certain amount. I would say that there is about 10% of the energy as elastic energy yet on the spring, and that makes the internal energy of the system equal to 90 degrees, 90%. Right? So that's how you do number 2. Okay? Now for number, I think it's number 4, the one that comes next. Let me check. For number 4, a ball rolls to a stop on the floor. Very easy. See, since the ball is rolling on a horizontal floor, we immediately can assume that the height is 0. You can place the 0 height anywhere you want. That's a convention. So in our case, it will be that surface. All right. We can also say that since the ball is not being stretched or compressed, the elastic energy will be 0 for all points, and it's not being burned, right? There's no chemical reaction. The chemical energy remains 0. It's not 0, but we're gonna set it to 0 because anyway it doesn't matter. We're not using it. All right. So the ball is moving the fastest at point A, as you can see, right? So let's assign internal energy to 1, as we have done before. So that means that 99% of the energy is in the motion of the ball. As you transition to point B, you can see the ball has lost some of the kinetic energy. So let's say it still have about 40% of, it could be 45%. So we're estimating the number, right? Estimating the number. So it's not the same exact value, but it's around a certain amount that is considered reasonable. All right, so let's assign it to 45 degrees, 45%. And so that means that the internal energy will be about 55. Why the ball is slowing down? There is friction between the ball and the surface. There's air resistance. And these two are taking the mechanical energy of the ball down to the atoms. Because friction generates heat, and the heat is translated into the motion of the atoms inside the substance. Right? That's what we call internal energy. If you can see at point C, the ball is not moving at all, so the kinetic energy must be 0, and all the energy stored in the ball, or the system, which is the ball, the air, the planet, etc., the surface, it's going to be 100%. All the energy is gone to the atoms. That's making the ball warmer, and the environment. Okay, so that's how you solve for number 4. For number 6, and the numbers are not distributed even. Okay, an object rests on a coil spring and is then launched upwards. So what's launching the object? Well, the spring is contracting, it's compressed. When you release the spring, it pushes on the object flies up a certain height, and the story ends right there. We don't know what happens after that. So you can see the object is not being burned, so the chemical energy is 0. So usually what I do is try to get rid of the storage mechanism that is not used. And you can see that we can assign a 1 for internal energy, and then we can assign a 2 for the second point B, and then we can assign a 3% to point C increase, in internal energy. If if you look at the picture, you can see that the object and the spring and the air and the earth, the system is touching the ground. So let's consider that the potential energy is zero. And also let's consider that this is not moving, which is true. So since it's not moving, the kinetic energy is also zero at point A. So all the rest of the energy is stored as elastic energy on the spring. That's why you see 99. All right. If you look at point B, you have an arrow telling me that the object is already moving up, and then also you can see that the height the object is increased. Since the spring is completely relaxed, no more energy stored on the spring for for B and for C. Okay? The spring does not do anything else. And so since it's moving and it's a certain height, but you can see the height is very close to the maximum height. So for potential energy, let's assume it's 80%. So how much kinetic energy we have? Well, whatever is left. So we're talking about 82. 100 minus 82, that will be 18. Is that correct? Right. So 80% of the energy is stored in the motion. This might not be too correct. We can switch, use different values. If you don't like to have only 18% of the energy as kinetic, you can move the numbers a little bit. But this is an acceptable outcome. At point C, you can see we have the object is not moving anymore, so the kinetic energy is zero. And so the rest of the energy stored in the system is as potential. That's when the system is at the maximum high. And so we're considering this is going to be 97%. So this is an acceptable outcome. Okay, so that's how you do number 6, I'm sorry. So let's move on to the next one. The next one is number 7. You have a piece of clay that is dropped to the floor. You can see at point A is not moving, so no kinetic energy. This is not burning. There's no spring. And let's assign the internal energy to 1%. Why not? So the rest of the energy is as potential gravitational energy. Okay? Almost all the energy is on the height. At point B, the object already lost some height because it's dropping and it's moving at certain speed. So for point B, all right, let's assign this to 0 and this to 0. Let's say that the internal energy is 2%. The percent of the potential energy is about half the original, so I would say 50%, and then the rest will be 48% for kinetic energy, which is adding up to 100, right? So you see, you can use easy numbers, so don't complicate your life too much. For point C, the clay is not moving. It's at the ground, so no potential, no kinetic energy. There's no chemical reaction going on there. There's no elastic energy involved. And all we can say is that 100% of the energy is gone to the atoms. That place is warmer now. So that's how you do number 7. For number A, we have a car that is moving at the same velocity. How do you know, mister? Because the arrows have the same size and the images are spacing out evenly, approximately, right? So, well, we can say that there is no elastic energy associated with the motion of the car that we can tell. If the car is on the ground all the time, it's level, right? We can say that we can set that height to 0. So the potential energy can be considered equal to 0. And then we have, let's assign a 1% to the internal energy, point A. And let's say that the kinetic energy of the car, it's about 60%. Why, mister? Well, because a lot of energy is stored in the chemical bonding on the of the molecules of gasoline in the gas tank. So I will assign 40% of the energy to the gas tank as chemical energy. As the car moves from A to B, you can see that the kinetic energy have to remain the same since it's moving at the same speed, same mass approximately. And let's say that the chemical energy is used up to all the way down to 35%. So 5% is used. So that tells me that the internal energy of the car has increased. So we're talking about 60, 35, that's 95. So now we have a 5% internal energy, right? So you can see also, well, at point C, you have the same speed for the car, but now it's using gas continuously. So now the chemical energy stored in the gasoline tank is 30%. That means that you have a 10% amount for internal energy. So that's how you do number A. All right. Let's do number 9. For number 9, you have a baseball that has been thrown up. So you can see at point A, the baseball is moving very fast. And as it goes up, it's slowing down until it gets to point C. At point C, it stops going up. That's the turning point, and then it starts coming down. And as it comes down, it's accelerating. So it's speeding up. It's going faster and faster. All right. So we need to reflect that in these 5 points: A, B, C, D, and E. At any moment, the ball is burning, or it is compressed or stretched. So we can set the elastic energies and chemical energies to 0. They're not part of this process. To simplify, you always try to see what you can discard. All right, so now at point A, the height is minimum, but the speed is maximum. I will assign a 1% for internal energy at point A, and that will increase by 1 at point B, and then 3%, point C, 4%, point D, and finally 5% at point E. All right, so as I said, a lot of kinetic energy, a little bit of potential energy. So let's say that we have about 69% of the energy as kinetic and 30% of the energy as potential at point A. That adds up to 100, right? At point B, it's a lot higher, almost to the maximum height, so it's moving a lot slower. So I would say about 80% of the energy is as potential, and then, well, 80 plus 2 is 82, so you have about 18% of the energy as kinetic. When it gets to point C, most of the energy is in potential, very small amount as kinetic. So I would say like 90% or even more. 96% of the energy is as potential, all right? 96 plus 3, 99. So only 1% of the energy is in the form of kinetic, barely enough to move around to the side. At point D, look at point D in the picture, you can see it's going down half the original or the maximum height. So I'm assigning 50% of potential energy for point D, and 50 plus 4 is 54, so I get 46, right? 46% to add up to 100%, if I'm wrong correctly. Yep, so that's for point D. And for point E, it's very similar to A. The only difference is that at A is going up, but at E is going down. And the other difference is that it's been moving on through air for a long time, so now you have 5% of internal energy. All right, so, but if you look at A, the potential energy for A was 30%, so that's what I'm going to assign here. And then for kinetic energy, we just make the difference. So it's going to be 65%. All right, so that's how you do this one, number 3. What do you think? All right. So that's why these are called energy flow diagrams, because you can see how each kind is flowing, changing to the expense of the other ones. If one increases, the other one can, decreases, and so they are kind of related. Okay, they're kind of related. All right, the last one is this one, and this one is a super ball that is dropped and bounces up and down. What would be the solution for this one? Well, what things can we discard here? The only thing you can discard is the chemical energy, because all the others are involved. So you can say that there's no chemical reaction, there's no burning for this ball, so we can set these energies to 0. Now if you look at points A, C, and E, these are maximum high points, but the maximum high is decreasing over time due to a loss of energy, in part because of the air resistance, and also when the collision happens at points B and D, there's a loss of energy when the ball interacts with the surface there. Some energy of the ball, especially the kinetic energy, is lost in the collision. To produce the sound of the collision, it goes to the surface, etc., etc. All right, so let's add internal energies. And we're going to do the same, 1%, 2%, 3%, 4%, and 5%. Well, let's work on a point A. There's no collision, so the elastic energy is 0. But most of the energy is in the high. So I would say there's still some kinetic energy because it's moving to the side, right? And you can see the pictures are evenly distributed, so it's moving to the side at the same speed. So I will assign about 5% of kinetic energy. The rest is potential. So we're talking about 94%. As the ball moves to point B is a turning point. It's not really moving, it's compressing and then stretching. So there is elastic energy associated there, but barely kinetic energy, so I'm going to just put the kinetic energy to 0. Also, the ball is colliding with the ground. We can set the ground so the potential energy is 0. And you can see that the rest of the energy is stored in the deformation of the ball, and then it springs back, right? And releases that energy again. But we're talking about 98% of the energy is as elastic energy, right? Well, you can see at point C, the object is back up, but the high it gets is lower. Why? Well, because there is some energy that is being passed to the atoms. So now the system has less energy to deal with. So for potential energy, we cannot get 94%. So we're gonna, for kinetic energy, we are going to assign 5 as before. And by the way, for E, it should be also 5 for kinetic energy. All right. Since we're talking about point C is not colliding, so this is 0 elastic energy. Say for point E, 0 elastic energy, and then we can assign a value for the potential energy. So we're talking about 100 minus A, right? 100 minus A is 92%. Compare that to 94. That's why it's not as high. At point D, there's a collision, potential and kinetic energy can be considered zero. You have 4% of the energy as internal, 96% must be elastic. Compare 96 to 98, right? It's less. As the ball bounces off point D, it goes back up to point E, and at point E you can see, you can make up the number already, because you have 5 kinetic energy and 5 elastic energy. That makes 10. 100 minus 10, 90. And so that's the answer for the last one, number 5. So just notice how the numbers are reflecting what's going on in the picture. From A to C to E, the potential energy should be less and less, since it's not gaining the same height. It's losing height. So it goes from 94 to 92 to 90. Notice that because of the pictures are showing me that the ball is moving evenly to the side, same speed, then the kinetic energy should remain the same for each of the cases. Okay? And notice also that after the first bounce, some of the energy is lost to the atoms. So when the second bounce happens, you get less elastic energy available. And well, that's it. That's how this is done. So I hope you understood what we did, and I hope you can use this to complete your assignment and turn in your assignment for a grade. Thank you.